So good afternoon, everyone. Can you hear me? Okay. All right, thank you. Okay, so I'm supposed to prepare for the fourth week of this thematic month. And I will speak today on complexity theory, algorithmic complexity theory. On Thursday, also, I will speak on information theory, something like this, randomness, let's say. And also this afternoon with Alexander Chen, you will have an exercise session on these topics and also on information theory. All right, so let me begin with a very brief historic reminder. Okay, so don't hesitate to ask questions first, and I hope it will not be too fast for those who don't know and too slow for the others. Okay, let's try it. So, quick historic reminder. Actually, the concepts that we will see today can date back, let's say, to the early 20th century, when we didn't know what was an algorithm, actually. So the first question that we will ask is, what is an algorithm? Which is not an obvious question, actually. So in the early 20th century, for instance, Hilbert asked for an algorithm to solve Diophantine equations. So he was completely sure that such an algorithm existed, right? So history proved he was wrong, but he couldn't see that it was not possible because we didn't have a notion of algorithm. We had to wait until the 30s, so around 36, for instance. Okay, 36, 37, you have Church and Turing that proposed the first correct, let's say, notion of algorithm. And the notion that we will see today is actually from Turing, and we will see the Turing machine. This will be our model of algorithm, okay? So once we have this notion of algorithm, people asked what is computable, what can be solved by algorithm. And actually in the 70s, 1970, Matyasiewicz showed that the problem of Hilbert was not solvable by an algorithm, so it was undecidable, okay? So it took 70 years to have this answer to Hilbert's question, in particular because we didn't have a good notion of algorithm at that time. Okay, so this was my historical introduction. And now we can turn to more concrete things. And we will see how to encode problems so that we can solve them by algorithms. So first, I should say what is a problem and try to give you an example so that you understand what it could be. So the problems we will see are decision problems. Okay, so decision problems. So yeah, I will speak of decision problems. Decision problems. So why decision? Because this will be a question. The answer will be yes or no. Okay, this is why it is called a decision problem. And so what is the general picture is that you have an input, let's say an integer, for instance, and you have a question here. For instance, is this integer a prime number? Okay, and then you have, of course, you are waiting for an answer, which is yes or no. Okay. So this will be what we call a problem or a decision problem, in particular in this case. And we have to understand how we can solve such problems. So there are two parts that we have to deal with. Okay. In red, we will have to understand what is an input. So I said it is an integer, for instance, in this particular problem. But actually, our algorithms won't take integers as input. They will take something which you can encode in the machine. Okay? So we'll have to understand what it is, and we will have to understand the mechanism to solve this question. And here we will need the notion of algorithms. Okay, algorithm, to solve the question. So here we will need an encoding. And here, the mechanism that will solve the question will be a Turing machine. And so the encoding is something to encode the integer, for instance, in a way that is understandable by the Turing machine. All right. Questions so far? Good. So, OK, so I think we can start with the encoding here. So it will be probably very common for most of you, I guess. We will encode the inputs by words on an alphabet. Okay, so here, the input, okay, see, yeah, the input is encoded by a word on an alphabet. So what is a word and what is an alphabet? So an alphabet is just a finite set of symbols, like sigma is a finite set of letters, let's say, symbols. And a word is just a finite sequence of symbols, okay? Finite sequence of symbols. So for instance, if you want to encode an integer in binary, we will need probably an alphabet of which is equal to 0, 1. At least it must have 2 symbols. Okay, example. You can take as alphabet 0, 1, and you can encode, for instance, an integer like in binary, something like this, which is a finite sequence of bits. Okay, you could take, of course, different alphabets. You can consider, for instance, the words over the alphabet AB, which is just a sequence of A and Bs. Okay, so now we need to understand how to formalize what is a question. So the problems, the decision problems, we need to understand how we can formalize it. And it will be, since it is a question, we just have to encode what are the inputs whose answer is yes. Okay? So we will just have to give the set of inputs for which the answer is yes. And this is what we call a language. It's just a set of words. Okay. So a language is just a set of words, and this will and this will encode our decision problem. So a decision problem is just a language. And what is a language? It is a set of words. So for instance, if we take the example of the prime numbers, we will encode them, for instance, in binary. We could use other encodings, okay? But let's say we will encode them in binary. And this will be something like, for instance, U in, so words over 0, 1. So we will note 0, 1 star for the set of words over 0, 1, such that U in binary, so if you look at it as a binary integer, is prime. All right, so this is the way we will formalize the decision problem of primality. So far, so good? Yeah, okay. Okay, so now that we have words, inputs and question, we need to understand what is an algorithm to solve this kind of question. Okay, and so this is maybe a bit more complicated for the one who haven't seen this before, but hopefully we'll manage. And I will speak of a Turing machine. So what is an algorithm? For us, think of a program in Python or in Java, whatever. And we want to model this kind of behavior. Okay, what can you do with the program? And actually, so it's interesting to see that historically, the Turing machine is far before the programming languages, like 1936, something like this, far before the first computers. So that's, and still it is interesting to see the Turing machine for the theoretical aspects it enables to show. Okay. So let's start with the model, so computation model. And as I said earlier, there are several computation models, but we'll stick to the Turing machine, which is probably the one which is closer to what we have in modern computers, let's say. Okay, so what is it? You have tapes. Okay, you can have several tapes. Each tape is split with an infinite number of cells. Okay, so infinite tape 1. You have an infinite number of cells. Here tape 2 also. Okay. And each cell can contain a symbol of the alphabet or can be left blank. So either you have an empty cell, which is denoted by the blank symbol, or you can have, for instance, if we are over the alphabet 0, 1, you can have a symbol of the alphabet. Okay? You could have this, for instance, this content for the tape. All right? So each cell is either a symbol or left blank. And the same for here. Suppose that the second tape is all empty, and you would have this configuration. Okay? Now we want a mechanism to read the symbols and to compute something out of these symbols. Okay. So we want what we call a head. Okay. So a read and write head. On each tape, we will have a head that can read the symbol in the cell here. So this is the head 1, and this is the head for the second tape. And the head can move left or right, or stay on the same cell at each step. Okay. All right, and then how can we compute with such a mechanism? Actually, we have, for the whole machine, we have a state Q that will evolve during the computation. Okay. How will it evolve? Actually, it will evolve as a function of what the previous state was and what is read on the tape. So let me do an example, and then we will try to formalize this. So let me give here maybe an example. So example. We want a machine that decides, so I didn't explain what it was, for instance, for the moment, but don't worry, I will. That decides the following language. Very easy language. I want the set of integers in binary which are even. Okay, so binary encoded. Integers encoded over 0, 1 as binary integers. Okay, U in binary is even. So this is a decision problem, and this is very easy because deciding whether an integer in binary is even is just deciding whether it has a 0 at the end. Okay? So it's just things like this. Okay, U0, where U. All right. So now we just have to decide whether the word on the tape is ends with a 0. So the configuration, the initial configuration is the following. You have on the tape, on the first tape, you have the input word. Okay, so for instance, you have 1, 0, 0, 1. Okay, let's say 0. Okay, it is in the language, it is even. And then we have blank cells. And the initial configuration is such that the head of the first tape is on the first symbol of the word, the input word. All right? So this is the initial configuration. So we always have the input word on the first tape. Okay. Now what can we do? We will, informally, we will just have to move the head here, cell by cell on the right, until we reach the end of the input. So how can we see that we reach the end of the input? When we arrive at this first blank symbol. And when we arrive at this first blank symbol, we can just get back one cell on the left, here, and we are sure we are at the end of the word, and we can just check whether it is 0 or 1. Okay, so very easy. So this is what we will formalize now. So I just said that the initial configuration is the following. Okay, so the initial configuration, this is the word, the input word is written on the tape number 1. And all the other cells are blank. Okay. So this is the what I wrote here. Okay, and the tape, the head, sorry. The first head is on the first symbol of, so the input word, which is called usually X, here. Okay. So this is the initial configuration. Now, how does it evolve? Okay, sorry. And the state of the machine is some initial state, Q0, which is a particular state in the set of all states, of the possible states of the machine. Okay? Now, it will evolve according to a transition function, okay? According to a transition function, which is usually denoted by delta. And it should describe the behavior of the machine. So what do we have? We have, okay, let's go here. At each step, we are reading the content of the cells that are pointed by the heads, okay? And we are in a particular state. From these informations, we must say what is the behavior of the heads, what is the new state, and what do we write in the cells. Okay? Of course, these cells can be, you can write something instead of the existing symbols here. The idea is just as if you had a paper and you can just write your ideas and just erase what you had written and so on. So you can read a symbol and, of course, write a new symbol instead of this one. Okay? So this is exactly what a delta should describe. So you take as input, your function takes a particular state, which you are in. It takes the different symbols that are read by the heads. So the symbols are from the alphabet sigma. And you have, let's say, k tapes. So you have k symbols. Okay. So I forgot to say, let's say k is the fixed number of tapes. So you have k heads and k symbols that are read. And then what will this function do? It will tell you what is the new state. Okay. So it will evolve in a new state, q. You have to describe how the heads move, okay, and what you write in the cells, okay. So you have k cells that you have to write into. Okay, so you write a new symbol here, and so on. So you will have k symbol to write, and also k moves to encode. So the k moves will be either you go left, or you stay where you are, or you go right. And since you have k heads, you have to encode k moves. Okay, and then your machine evolves according to this rule. Is that more or less clear for everyone, or yes? Okay, so yeah, please.
I don't understand what the Q is.
So okay, yeah, Q is the set of states of the machine. So this is a finite, actually, I forgot to mention it is a finite state.
What's a state?
A finite set, sorry, of state.
The machine, that's all you remember in your memory, internal memory. You have a tape and you loop the word. And then you have some internal memory, which can be infinitely many states. You cannot remember infinitely many things.
So actually your infinite memory is on the tapes. Yeah. And your working memory, let's say, which is finite, is encoded in the states here.
So it's essentially additional information to the one I'm given in the tapes.
Yes.
It's not even. It's your kind of local.
I made it.
So, so it's kind of, it's more like, I would say it's more like the behavior of the machine that can, maybe I should give an example here. Yeah. This example, maybe you will understand better what is the state, okay? So let's try to understand what is the transition function for this machine. Here the goal is to start, you start with the initial state Q0, okay? And you want to evolve. The moves are go to the right until you reach a B, okay? Then, so this will still be in state Q0, so I will write it, but you will still be in state Q0 until B, but then in B you have to change your behavior, and you will change your state to say, okay, now I will go backwards, okay? So you will go in a state Q1, for instance, you will go one step backward, and then you can decide if you accept or not. So kind of the states are kind of the behavior of the machine, okay, something like this, okay? So let me write it. So here, what we would say is that if you are in state Q0 and you read a 1 or a 0, and one or the other, and it doesn't matter, you will stay in state Q0, okay? You will write either, I mean, you leave the symbols as they are, either the 0 or 1, you don't touch the symbols, and you go right. So this would be the transition if you are in state Q0. Now, if you are still in state Q0 but you read a B, so you read now a B, you are at the end, just after the word actually. So you need to get back one step left. So what you could do is you go in a new state to say, okay, I've reached the end of the word, now I have to change my behavior. It's like, let's say, the different lines of a program, something like this. The states can be thought as roughly as the different lines of a program, which is not the same as the content of the memory. I don't know if it's okay. And now, so if you are, if you have reached the end of the word, you can, leave it blank anyway, and you go left. So now you are here. In state Q1, okay? You have changed your state, so you know that the behavior won't be the same in state Q1 as in state Q0, okay? Because Q1 is just saying that, okay, I've reached the end of the word. I have to do something different. And now, if you are in state Q1 and you read, for instance, a 0, then you want to accept, okay? You want to accept the word. So you will go to a state which is called usually QA, Q accept, and you write whatever, it doesn't matter. And you stay. But if you read a 1, you have to reject because it is not an even number, and you will just go to a state which is reject. And so you see that you have 3 particular states, Q0, which is the initial state, and 2 particular states that are accepting or rejecting state, and which end the computation. Okay, so accept or reject. So is it more clear now?
So can I think of Q0 as saying, okay, I'm like actually I'm in my word and just should keep walking, and Q1 is like I reached the end of my word. So
in this particular case, yes.
Then,
in this particular case, yes, but it's not always the case. Okay, yeah, exactly. It's kind of a change of behavior, or let's say you change you call a function, for instance, in your code. Then you will probably have to change your state to remember that you are calling a new function and doing different stuff. Okay, something like this. Okay. Yes. Okay. So at the end of the execution, other questions? Is that clear? So at the end of the execution, sorry, you are in a particular state, which is either QA or QR. So this, I mean, the end of the computation is when you reach one of these states, and in that case, you either accept the word or reject the word. Okay. So at the end of the computation, you are either in QA, which is the accepting state, you accept the word, or you are in a QR, which is the reject state. Okay. So now you see that with such a mechanism, you can take any word from a language, and at the end, you either accept or reject the word. And this way, you can actually decide languages. So that's what I have to do right now. Okay, let's try this, yes. All right, so so what is the language that is decided by a Turing machine? It is just the language decided by the Turing machine is just the set of words that are accepted. So the set of words such that M on input U accepts. So ends in the state QA. All right. So this is our notion of algorithm. Okay. And now we can try to understand what is the power of this kind of machine. So we've seen an example here, and actually it is, I mean, with some practice, you can convince yourself that every program that is written in C or in Python or whatever can be simulated by a Turing machine. Okay? So this is kind of a universal model of computation, let's say. So I stated informally, so every program in, let's say, Python or Java or whatever can be let's say, simulated by a Turing machine. Okay. So this is not a proof, of course. For this, I mean, it can be proved actually, but it is necessary, I think, to try to convince yourself by doing several examples. Maybe examples more complicated than this one. For instance, you can try to give a Turing machine for the following problem. So exercise, yeah. Build a Turing machine for the language. You have the alphabet has 3 symbols, 0, 1, and sharp. And you have this, where X, Y, and Z are integers coded in binary, okay? And you want to see, for instance, whether the addition of X plus Y is equal to Z. Okay. So this is very simple, of course. But for a Turing machine, that's not so simple. So I encourage you to try to do this kind of exercise to see that indeed you can execute this kind of program. Okay.
Are you allowed to enlarge the alphabet table?
So yeah, okay, I didn't go into full details because I don't have enough time. But actually, yes. So the question is whether, okay, you have an input alphabet which encodes your words. For instance, here you have 0, 1, and sharp. But maybe you want when you are working, you want to use other symbols, okay? And actually you can. You can use other symbols that are not in the input alphabet. You have kind of a working alphabet, and in particular, the working alphabet contains the symbol blank above, which is not in the input alphabet. Okay. Yes. So here, just to summarize, you need to build a machine that has a finite number of tapes that takes as input, it means on the first tape it has this word encoded on an alphabet with 3 symbols, and you have to decide whether this is true. That is to say that at the end of the computation you are in the state QA if this is true, or QR if this is false. Okay. Okay, so I hope this is clear to now. Yeah. Yes, please.
Just a question, when you reach QR or QA, you stop everything?
Yeah, you stop everything, exactly. Yeah. Exactly. Good. So when this was introduced, people asked, what is the power of these machines? What can they compute? Okay. So Hilbert, I think, was not in his head, but I think he thought that algorithms could solve any mathematical problem. And actually, he proved wrong afterwards. And indeed, this is what people studied first, of course, so computability. So what is the power of such machine? So what can Turing machine compute? And actually, the answer is not everything. Actually, not a lot. And I will try to give you an example of a problem which is not solvable by this kind of machine. So it's not solvable by our computers now, because we are just simulating, let's say, this is just equivalent to a Turing machine, what we use on our computer. Okay, so let's try to understand that now. And actually, this is rather easy to see. I mean, the proof is not hard, if you don't go into the details, let's say. And it was roughly the result of Turing in his paper of 1937 to show that there was problems that were not decidable by Turing machines. So it means that whatever the computation time, you cannot have an algorithm for these kind of problems. So I'm just doing this example because we will see a similar kind of reasoning afterwards. So theorem, the problem. So this is called the halting problem. So actually, I'm a bit cheating here. This will be just a variant of the halting problem, okay? So the halting problem just asks whether you're given a machine, the code of a machine, a Turing machine, and you want to know whether it stops on an input, okay? So the variant we will see is the following. You will have as input, so you need to encode your transition function and the alphabet and so on in binary, let's say. Okay. So you have the code of a machine like this. So this is the code of a machine M, and you encode it on, I don't know, on the alphabet, for instance, is 0, 1. Anyway, it doesn't matter. Okay. So you take as input the code of a machine, so a word that represents a machine, okay, and you wonder whether, the question is whether when you execute M on its own code, okay, whether it rejects. So this is a problem, okay? You just want to know whether M on its own code rejects. So its code is a word over 0, 1. You take the machine, you execute it on this particular word, and you want to know whether it rejects. Okay? Okay, so this problem is undecidable. So what does it mean? It means that there is no Turing machine that can decide this problem. It's undecidable. And how can you prove that? So actually, this is a kind of, this is called diagonalization, but here it is kind of hidden. So sorry about that. But anyway, so this is diagonalization. Okay, hidden, let's say, because we don't really see it. Diagonalization. And the proof actually is super easy. You suppose, by contradiction, that there is a machine M0 that accepts, that decides this problem. So if, by contradiction. So if some machine M0 decides H, what does it mean? It means that it should accept every word in H. So on the first, okay, actually, sorry. What does it mean? We will look at what is the behavior of M0 on its own code. Okay? So M0 on its own code. It accepts if and only if, so by definition of the acceptation of a machine, it will accept exactly when the word is in the language. Okay? Exactly if, only if and only if, sorry, M0 is in H. So this is the definition of a machine deciding a language, right? And now you take the definition of H, and you see that this is exactly equivalent to M0 on its own code rejects. And you have a contradiction. Okay? You have M0 on its own code accepts if and only if it rejects. So this is not possible. Okay? Contradiction. Okay, so the proof of actually of Turing was much more involved because the language was not exactly this one. It was a more important one. But you can show actually that most, I mean, all problems that are non-trivial properties of machines, the behavior of machines, actually are undecidable. So this is Rice's theorem. So you can look at it if you are interested. But actually, it's kind of normal that many problems are indecidable because there are an uncountable number of languages and a countable number of machines. Okay. So most problems are actually indecidable. Questions so far? So here we've seen the computation model. If you are not very familiar with Turing machines, just think of your favorite programming language. Okay. And now, we have seen also that they cannot solve every decision problems. But we haven't said anything on the efficiency of the machines. And actually, in the 60s, let's say, computers began to develop, and researchers begin to wonder whether what can be done efficiently on computers. Okay, they are very weak computers at the time, and they wonder, okay, you cannot solve these problems. You can solve many other problems, of course. For instance, parity here. But what are the problems that can be computed efficiently? So the problem turned to you focus on the problems that are decidable. They have algorithms, okay? But you wonder, do they have efficient algorithms? So that is, okay. That is the purpose of algorithmic complexity. So this was computability before, and now we turn to this complexity, sorry. And the question is, what can we compute efficiently? What languages can we decide efficiently? All right. So let's start with time complexity. So in this course, I will only speak of time complexity, which is a time constraint on the algorithms. We want to understand what kind of languages can be decided in short time. Okay? There are many other complexity measures that we could use. For instance, space complexity, which is the number of memory that you use, but I won't speak about that. Okay. So here, let me start a chapter on time complexity. Okay. So of course, when you run your program, any program, you probably want it to be efficient in the sense that you don't want the answer to come like 2 weeks after that you run your program. So the notion that we want to capture here is how many time does it take for the algorithm to run on a particular input or in general. So this is not, I mean, this is rather natural. We want to count actually the number of steps that the machine takes to go to the final state QA or QR. Okay? So definition, the time complexity of a machine M on an input X, okay, is the number of steps of steps in the execution M of X. All right? So you count the number of steps, number of transitions that you take. So far, so good? Yeah. Okay. But of course, we don't want to measure the complexity of M on a single input, but we want to say that this language is easy, for instance. This language has an efficient algorithm. So we want to speak of the complexity of a language. Okay. So we don't want to focus on a particular word. And now, what we will say is that imagine you have a problem, that's, for instance, this one, or maybe the addition that we've seen before, or primality. You want to decide whether an integer is prime. Of course, probably your algorithm will take more time on longer inputs. So the idea is just to measure the complexity, the time complexity of the machine, depending on the size of the input. Okay? Because it's rather natural that your program will take more time on integer of 100 digits than on integers of 3 digits. Okay. Okay, so that's what we will do, actually. So the complexity of a machine M is the function, let's say, t of n. So this is a function of, t, okay. Let me write it like this. Okay, from the natural numbers to the natural numbers, which takes as inputs a size of input. Okay, and what do? We want to understand how long does it take for the machine M to compute on inputs of such a size. And in this framework, we are interested in the worst case. So what is the worst input of size n possible for my machine M? Okay, so we just associate it to the max of all the, so for the max of on all the words of size n. Okay, so you take the max over all the words of size n of the time of the execution of M over U. Okay, so you take the maximum of all over all the inputs of size n. Sorry. Okay, so so this is our measure of complexity. Is that rather clear? Yeah. So here, for instance, what is the number of steps that we will have on an input of size n? Actually, we will do so n steps to go here, and 1 step to go backward. So this will be n plus 1. Oh, yes, yes.
This might be a silly question, but you assume the size on everything, right?
You assume what? Size of?
That it doesn't keep running forever.
Yes, yes, yes. Yeah, okay, I just said it. I didn't write it. But actually, yes. From now on, we suppose that our language is decidable and that the machine always halts. Okay, yes. So good question, actually. We have seen that every language is not decidable, but in the complexity framework, we will just be interested in decidable languages, and therefore we will suppose that our machine halts. Okay. So here, exactly, in our context, it won't be infinite here, in other words. Yeah. Good. All right, and then from that, we can define complexity classes. So, okay, so a complexity class, what is it? It is a set of languages, a set of problems. We will just actually gather problems with similar complexity. So we'll say, for instance, that if you have such a function here, the class d time of t, let's say, okay, d time of t, will be the set of languages that have algorithms running in time t. Okay, so this is a set of languages decided by Turing machine in time. Alors I will put a big O of t. Okay, it's like this. We usually write t of n because just to emphasize that it is a function of the natural numbers. Okay, so why is there this O of t? This is because actually, okay, this is not important for the lecture, but just tell me why. Because actually, if you have a machine, so not this one, but a more complicated machine that takes, let's say, time 10 times n squared, for instance, okay? So t of n is 10 times n squared. Actually, you can speed it up. You can speed it up by enlarging the alphabet. You can do a kind of parallel computation to speed it up at the price of enlarging the alphabet a lot. But you can just speed it up, of course, by a constant factor, okay? So it doesn't mean anything to forget. I mean, it means that if you are in time 10 times n squared, then you have a machine working in time n squared also. Okay, so that's why we have actually the big O notation here. We don't care of the constants. We don't care of the multiplicative constants because we can speed the computation up. Okay, now you can forget this remark. Okay, so is that clear, this definition? So for instance, this language here is in d time of n. We've seen it is in, it can be decided with a Turing machine in n plus 1 steps. So it is in big O of n, and so therefore it is in this complexity class. It is, of course, also, just to be sure that we are on the same page, it is also in this class, of course, okay? Because we have the inclusion, this one is included in this one, of course. Okay, if you have more time, of course, you can decide, I mean, you can stop before. Okay? Okay, so if we have these complexity classes, we can actually define usual complexity classes and deterministic complexity classes, which is the class P and the class X. And then we will show that these classes are different, which is not completely obvious at first, but they are. Okay, so when we have this definition, we can define the class which is called P for polynomial time. Okay, polynomial time. Okay, actually deterministic polynomial time. Polynomial time. What is it? It is the union. Okay, I did the union, if you want, of over all k of d time of n to the k. So it is the set of languages that have an algorithm working in time n to the k for some k. Okay, meaning that it has a an algorithm which works in polynomial time. I will abbreviate this by this abuse of notation here and to the constant. Okay, this will be the union of the d time n to the k. All right. So why do I introduce this class? Because it is considered, in theory, as the efficient problems, the problems that have efficient algorithms. Okay, problems that have. So I put quotes here. I will explain later on why. Efficient algorithms. Okay. So why did I put quotes here? Because when you have an algorithm running in time n to the 1000, it's not at all efficient. Okay. So in practice, it's not efficient at all. But in theory, it has good properties, and it was considered in the 60s like the right notion of efficiency. Okay. So example of problems here. So I said this parity, of course, is in P. Okay, this is a problem from P because it has a machine running in linear time. Okay, you can try other problems like addition that we've seen before. It is also in P. So the problem that I gave you as an exercise, it is also in P, of course. You can just do the algorithm of the primary school, and it gives you an algorithm working in polynomial time. Okay. So you have also multiplication, integer multiplication. Okay, you have matrix multiplication, for instance. So why matrix multiplication? Because you just make a polynomial number of additions and multiplications. So it remains polynomial time. It remains in polynomial times, and so on. So many efficient algorithms on graph also that can be done in polynomial time. Okay? So this is considered as efficient algorithms. And now another class which is not efficient at all, which is called exp for exponential time, and which is in d time, which is actually d time of 2 to the poly. So an exponential number of steps. And of course, you know that, for instance, if you have a number of steps of 2 to the n squared, it is a very, this is a huge number of steps, and it will take, for instance, if you have 2 to the n squared, for inputs of size 10, which is very small, it will take 2 to the 100 steps, which is far more than we can allow in the universe or whatever. So it's not efficient at all. Okay. And what we will see afterwards is that exp. So we could wonder whether we could maybe give more efficient algorithm for this class. Maybe we can collapse it to P, but actually we cannot. Okay, this is what we will see later. Actually, there are problems of X that are not in P. But I want to give first some examples of problems here. And, yeah, oh, sorry.
Can I ask something?
Yes, sure.
So when we say that addition lies in P,
Yes.
that means that we make it into a yes-no problem, right?
Yeah, actually, the problem that I had in mind was this one. The one I gave as an exercise. Yeah. Such that X. And the same for multiplication. That's what yeah. But, okay, I just focus on decision problems, but you can have the same notion for functions, actually. So you could also speak of polynomial time functions and so on. Okay? But yeah, for this lecture, I just focus on this. All right. So let me give some examples of problems here. So where do you place the problem primes? So primality. So primes is the following problem. You have an X in binary, which is supposed to encode a natural number in binary. And the problem is whether X is prime. Okay? So the usual naive algorithm is to test all the divisors of X until square root of X, up to square root of X. This is the usual naive algorithm for that. Where does this algorithm place primes? So you have, okay, I'm just writing it. So, okay, let's say naive algorithm. This is test all divisors up to root X. Okay, if you see that there is an integer dividing x, then it is not prime, otherwise it is prime. All right. So it takes square root of x steps, roughly, okay? Let's say. At least square root of x steps. Probably a bit more because you have to decide each time whether it divides or not. Okay. So where does this places primes? Does it place it in P or in X? Yes, in X. Why?
Because you have to write it in binary.
Exactly. So that's why I wanted to do this example. X is written in binary, so that the number of bits it has, the size of X, is actually log of X. Okay? The size of X is log of X when it is encoded in binary, so that actually this algorithm, working in root X steps, takes, as a function of n, the size of the input, it takes actually root of 2 to the n, okay? Okay, which is exponential, which is exponential. So this particular algorithm places primes in X. And up until 2003, we didn't know better than this. But actually, in 2003, you have an algorithm by Agrawal, Kayal, and Saxena, which places in P, which is a polynomial time algorithm. Okay. But which is not as easy as this one. Okay. All right? Yes? Yes. So before AKS, we only had randomized algorithms working in polynomial time. And we didn't know better than an exponential time deterministic algorithm. But it was a kind of a breakthrough. They just gave the deterministic algorithm running in polynomial time for primes. Yeah. Yeah.
And it's used a lot in practice?
I think at first not. And I think then they just got better. I mean, the complexity got better. And I think it's kind of usable in practice now, but it's far less efficient than randomized algorithm. Okay. Yeah. Okay, so what else? What else as an example of a problem in Exp? Let me give another example. Sorry. So I just introduce a problem which is not capturing actually the class X, but I'm just introducing it because we will see it later. So the language click is you have as input a graph G. So for instance, a graph like this. Okay. And an integer k. And the question is whether G has a clique of size k. So what is a clique of size k? It is a set of k vertices that are all connected together, pairwise connected. Okay. So here, so k vertices that are pairwise connected. So in this example, which is probably a very bad example, but anyway, there is a 3-click here, okay? 3-click. And it has no more than, I mean, it has no click of size more than 3 here. Okay? And so this problem is, okay, it is very particular. I will go back on that later. But actually, the best algorithm we know, roughly, is to test every set of vertices of size k and to see whether it forms a clique. Okay, the algorithm. Okay, let's say best. It is not exactly the best one, but let's say we don't know much better than this. It is just test all sets of k vertices. and check whether they all are connected. And if you do that, for instance, if you have, so the complexity is something like k choose n, okay? N choose k. Okay, anyway, this, n choose k. And this can be exponential if k is of order n. Yeah? Yes, please.
The input is the number of vertices.
So the input is an encoding of the graph here. Let's say the adjacency matrix of the graph. Okay. So an encoding of this graph. So it is of size, let's say, n squared, where n is the number of vertices, together with this integer encoded in binary, let's say, or in unary anyway. It doesn't matter. Okay. Is that clear? So let's say, yeah, the size of the input is kind of the number of vertices squared. Okay. And so compared to this, for let's say k is n over 2, where n is the size of vertices, is the number of vertices, it is exponential in the size of the input. So, okay, so this algorithm places click in exp. All right? Okay. So let me briefly sketch why actually we cannot collapse exp to p. We cannot have much better algorithms for some problems in exp. We cannot have polynomial time algorithms. So I will just briefly sketch the proof and then go to another kind of computation, which is non-deterministic computation, to speak of NP, the class NP. All right. Okay, before I go on with the following theorem, do you have questions? Is that rather clear so far? Yeah. Yes, please.
The complexity heavily depends on the way how you encode your...
Exactly, yeah. That's what I wanted to show with this example of primality. If you encode it in unary, the size of x would be x. And therefore, the naive algorithm would be polynomial. Okay? But usually we don't encode it in unary, but we encode it in binary. And therefore, it becomes exponential, yeah, for the naive algorithm. Yes, you're right, yeah.
So by default, I mean, sometimes there's a natural way to encode a
Yes.
problem, but
If there is no natural way, you need to specify what is the way you encode things. Yeah. Thank you for the remark. Okay? Yeah. All right. So theorem. Okay. This is called time hierarchy theorem. And this is due to Hartmanis and Stearns in 1965. And actually, it's kind of the birth of complexity theory because it gives you a way to separate complexity classes. So it gives you a way to classify the problems, let's say. Okay? So the time hierarchy theorem tells you the following. If you have two functions f and g, which are functions, complexity functions, let's say, such that f is small compared to g, meaning this, f times log f is negligible. So g is large, if you want, in comparison to f. And actually, you have another condition on g, which I won't speak about, but g is time computable, which means that you can easily compute g of n, okay? Which is, and for polynomials, it's always the case. For exponential, it's always the case. So for most complexity function, it's the case. So you can just forget this if you want. You just have an f which is much smaller than g. Then d time of g is strictly larger than d time of f. So of course, this class contains this one because G is larger. But what the theorem says is that actually it is strictly larger. So there is a language here which is not there. Okay? And actually the proof goes exactly along the same way as the halting problem before, the undecidability of the halting problem. So actually there are details that I will omit because I don't have time. But the idea is the same, proof idea, sketch. So you take the problem L, which is the encoding, the code of a machine M, and you want to see what is the behavior of M on its own code. Okay. So if I stop here, it is exactly the halting problem that I've shown before. But now I just plug another condition. I just say this, f of n. Okay? So the n here, the n here is the size of the inputs, n. Okay? So n here is just the size of the encoding of m. And if you look at this problem, you can show that for some reason, to simulate this machine which you don't know in advance, you need a universal machine. Okay, I won't speak about that, but it takes time g, so f times log f. To simulate this, it takes time f times log f. Okay, the overhead is because m is arbitrary, and you need a universal machine to simulate this. Okay, m is not fixed, so you have an overhead. And the overhead actually comes from the fact that you want to have a fixed machine for L, but the machines that are encoded here can have an arbitrary number of tapes. So you want to simulate a machine with an arbitrary number of tapes by a fixed machine deciding L, which has, of course, a fixed number of tapes. So that's why you have an overhead, which explains the log f here. Okay. So this is in the time of G, because you just have to simulate the machine M on its own code, and to see whether it rejects. So yeah, this is easy to decide it in the time of G, but if it was in the time of F, you would have the same argument as before, and it's not possible. And you have so a contradiction if L is in the time of F. Okay, so okay, that's it. So you've built a language which is in the time of G, but not in the time of F. So I won't go more into details, but you have some technical details that you have to handle to prove this correctly. Yes?
Do you mean the time of f log f? Because right now I don't see how it takes into account the G at all.
Yeah, actually, okay, yeah. I mean f log f. But there are some details that I omitted, which makes it a bit more tricky. Okay. In particular, the constants before the f log f depends on the machine M. That's why what I've just written here is not very correct. But yes, the idea is that. Yeah, exactly. Okay. Okay, so I have 20 minutes to introduce NP completeness. Okay. But we'll manage. So let me speak of non-determinism. Actually, in his paper in 1937, Turing introduces non-deterministic Turing machines. Okay, it was not named Turing machines at the time, of course. Non-deterministic machines So he wanted to mimic the way you can reason. I mean, a mathematician can reason on a piece of paper. And of course, a mathematician on a piece that reasons, I mean, that proves a theorem on a piece of paper, will not consider only one possibility when he has a choice. Okay, he might have choices in the proof, and he might consider this hypothesis better than this one. So he introduces machines that have some choices. Okay, instead of introducing deterministic machines for which the transition function is a function, he introduces machines for which the transition is a relation, actually. So you have several choices in the computation steps. Instead of going, for instance, here, when you are in state Q1, for instance, you might have the choice of keeping going on the right. Maybe that's not very interesting, but anyway. Or you might have the choice to go back to the left. Okay. So that's a choice that the machine could make. And so that's what is non-determinism. It means that at each step, you might have several options. Okay? So here, the transition function is a transition relation. Meaning that actually, instead of having just a computation path, one execution, you have several possible executions, and the computation path is actually a computation tree. Okay, so you have a computation tree. Like, for instance, you start from the input x, then maybe you have here two possibilities. For instance, you stay on the first symbol of the input, or you go on the right, or whatever. Okay, and here you have if you choose to stay on the first input, on the first letter, then you access a new configuration, which might also have several possibilities. For instance, you might have three possibilities from here, okay, and so on. So you have a computation tree like this, okay. So it is exactly the same as the deterministic machine, apart from each time here you just have only one possibility, but possibly several possibilities for the transition function. Okay. And in this particular case, how do we accept a word? Because you could have a path here in the tree which goes to reject state, QR, and another path in the tree which goes to an accepting state, sorry. Okay, oops. Okay, here you might have both possibilities. So what can you do in that case? So the definition is that in that case, you accept the word. So why do we choose that we accept the word as soon as there exists one accepting path? This is to kind of simulate the intuition of a mathematician that could solve a theorem. Okay, maybe he will prefer to go to this path because it seems more reasonable or whatever. And finally, if he finds a proof, even if the other paths are just dead ends, it's solved. I mean, the theorem is proved, okay? So you don't care of the other path if you have found an accepting path here. So as soon as you have at least one accepting path, you accept the word. But the theorem, for instance, if you think it is the proof of a theorem, the theorem is false if every computation paths are rejecting. Okay? That's exactly why we choose to say that the word x is accepted if, and only if, there is at least one accepting path. All right? Okay. So remark that this definition is not symmetric between accepting and rejecting. To reject, you have that all paths are rejecting. To accept, you have that only one path is accepting. Okay. Okay. So what is the computation time of this kind of machine? The computation time is just the depth of the tree. Sorry. The depth is just the time. It means that it is the maximal time of a path, of an execution path. Okay. And as before, we can define non-deterministic time, which are the problems, the set of problems of languages accepted by non-deterministic Turing machine. So this is non-deterministic here. Turing machine in time O of Tn. So does it make sense, or was it a bit too fast? Yes, please.
What happens if you take the time to be the length of the shortest accepting path?
I don't think so, because yes, okay, yeah, the shortest accepting path. The shortest path, it doesn't make much sense, because you could just add a dummy rejecting path of size 1. Okay, if you say it's the size of the shortest accepting path, if there is one, I don't know, it's a bit of artificial, but I'm not sure. I'm not sure it changes anything, actually. Yeah, not sure. Exercise. Okay. Yeah, is it roughly clear? So actually, I won't spend too much time on defining this particular model, because we have another characterization of this kind of classes. Oh, yes, sorry.
To solve the exercise, if the time is time constructible, then you can just artificially stop the execution after this many steps. And
Yeah.
if there is always an accepting path at this time, then you have a new machine where all the accepting paths are. Maybe I misunderstood.
We probably can do something along this. Yeah, we probably can do something along this way. Not completely sure. We can think of line. Okay. So yeah, I said that I won't spend much time on this computation model, because we have actually a characterization of these problems, which is, okay, I will call NP is the class of non-deterministic polynomial time. This is the set of languages which can be decided in polynomial time on these machines. Okay? And actually, as maybe you know, the question of whether this is equal to P is a central question in algorithmic complexity. So I will try to now understand, this is open, okay, but I will try to understand why it is important now. So I want to spend some time on the class NP itself, and then try to introduce NP completeness. Okay. Okay, so why, yeah, I said there is a characterization of NP in terms of deterministic polynomial time. And actually, a language L is in NP if and only if there is a language A in P and a polynomial P of n such that an input X is in the language L if and only if there is a certificate Y of polynomial size with respect to the size of X, such that the tuple XY is in A. So let me explain this characterization. You are kind of helping your deterministic machine here with a path Y in the tree here. You just say what is the path in the tree. You encode it in Y, okay? And actually it gives you what is the correct path to follow to reach an accepting state. Okay? And so this path here is called a certificate, let's say, or a proof. And what it tells you, actually, this characterization, it tells you that an NP problem is nothing else than a problem that if you give potential solution, Y, a kind of proof, you can easily check that it is a correct proof. So you have a theorem, mathematical theorem. You give me a proof. It is easy to check line by line if the proof is correct. Okay? Yeah. So this is what is the purpose of y. Okay. And actually, for instance, think of clique, the problem clique that we've seen before. If you give me the set of k vertices that I have to check, it is easy to check that indeed there is a clique of size k. You just have to check whether the k vertices that you gave me as a certificate are indeed connected, right? So think of a grid of Sudoku. It is not easy to fill the grid, but if you give me a possible solution, I can check that indeed it is a solution. I can check it efficiently. It is easy to check. This is exactly NP. Problems that maybe, for which maybe the solution is not easy to find, but at least if you give me a potential solution, I can say, I can verify whether it is a correct solution. This is exactly NP. Okay, and as I have argued, clique, for instance, is in NP. And you have other problems that are in NP, such as, for instance, the problem of satisfiability of Boolean formulas. So let me introduce this, because I want to finish on some well-known theorem, just on time, I think. So let me introduce this particular problem of satisfiability of Boolean formulas. As input, you have a formula phi, which is a Boolean formula. For instance, okay, I forgot to mention first order predicate, actually. Okay. For instance, phi of x1, xk is, I don't know, x1 or x2 and not x3 or and x1. Okay, something like this. Okay, you have such a predicate. And the question is phi satisfiable? Does there exist x such that phi of x is true? Okay. So this is the question. So far we don't know very good algorithms for that. The best kind of algorithms we know is we just test every possible inputs x. We just have to test every affectation. And there are 2 to the k affectations, possible affectations, so the algorithm is exponential. Okay? But actually, it is exponential, but actually it is even in NP. I forgot to say something which might be important. I forgot to say that, of course, P is included in NP because the machines here are more powerful. Okay? But NP can be simulated by just simulating every pass in the tree in exponential time. So NP, is contained in exp. So this is normal that this problem sat is in exp. Okay? But actually, it is an NP. It is an NP because you just have to give as a certificate the correct affectation for the variables, and then you just have to check that on this affectation, particular affectation, the formula is true. Okay? You see that? So this problem is in NP. And actually, it is very particular problem because historically it is the first problem, natural problem, that has been shown to be NP complete. So I will try to explain what it is. A theorem. So this is a theorem by Cook and Levin in the 70s. Okay, in the 70s, SAT is NP complete. It means informally that it exactly captures the power of NP. Okay, this is exactly the same, the full power of NP. So let me try to formalize that. So NP complete means it is in NP. So I've already argued that because you just have to give as a certificate the correct affectation if it exists. Okay. And if none exists, of course, it is not in SAT. Okay? But if there exists one, you give it, and you just have to check that phi is true on this particular affectation. And furthermore, NP complete means that every other problem in NP reduces to SAT, so is easier than that SAT. Okay? So every A in NP is easier than SAT. Okay, so easier than SAT, I need to explain what it is. But first, let me mention that it was not clear at all that such a natural problem existed. I mean, this is a very strong condition. You have to give an example of an NP-complete problem, which is harder, I mean, which is at least as hard as every other problem in NP. Okay? So this is not at all trivial. And that's why this theorem was most welcome. And before I go to the detail of this, I want to emphasize that actually, after this theorem, plenty, I mean, thousands of other problems, important problems in practice, have been shown NP-complete. Okay, so thousands, let's say, I don't know, hundreds at least, problems of importance in practice have been shown NP-complete. And for all these problems, we don't know any polynomial time deterministic algorithms, okay? And no deterministic polynomial time algorithm for these problems, meaning that probably they are difficult. But still, we don't know how to prove that NP is different from P. We don't know how to prove that. Okay. So we have kind of evidence that these problems are hard, but we don't know how to prove that they are hard formally. Okay. All right. So let me try to give the definitions, the definition of this reduction here. And first, I should mention that this. Okay, I should just emphasize before I give the definition that actually, if you want to prove that NP is equal to P, the NP completeness of SAT allows you just to give a deterministic polynomial time algorithm for SAT. So this is equivalent to give a deterministic polynomial time algorithm for SAT or for any other NP-complete problem. Okay? So that's why it is important to consider these NP-complete problems to solve this P versus NP question. And now I just give you the definition of the reduction and try to understand why it is interesting. Okay, so all right, so we say that a problem A, many one polynomial time, so this is for many one, this is for polynomial time, reduces to B if and only if, so there exists a function f computable in polynomial time so deterministic polynomial time. Okay, so just by a Turing machine working in polynomial time, such that if you want to decide A, you can do so by a pre-computation with F, and then run B. Okay, so that X, for all X is in A, if and only if F of X is in B. So if you look at it, to solve A, if you can solve B, you just have to make a pre-computation F of X and to run B, and you have the answer for A. So in that sense, A is easier than B. If you can solve B, then you can solve A. Okay? And this is the example, this is the definition of a reduction. And for instance, if you have the problem click, and the problem independent set, which is just as input you have a graph G and an integer K, and you wonder whether there is an independent set of size K, meaning K vertices that are all disconnected, okay, then you have just a reduction between the two, okay, they are equivalent actually, you have a reduction that goes along this way. I mean, f of gk is just, you take the complement of g and keep the same k. And as an exercise, you can show that it is a reduction from clique to independent set and also in the other direction, which is a very particular case. Okay, thank you. And sorry, yeah. Okay.
So we have time for short questions.
Thanks. So you say this reduction is polynomial and many to one. I see the polynomial, but not the many to one.
So why many one reductions here? This is because actually f is not supposed to be injective. That's it. That is just. I mean, maybe you can. You can see it like this. This is just equivalent to. Let me just write it correctly. So A. Okay, no. I will just mix it up. B is something like this, I think. Yeah. And okay, I don't see it. I don't see it right now. But it. So okay. So okay. And you see that you don't want f to have particular conditions. I mean, you don't want f to be injective whatsoever. So that's why it is many one reduction. You have other kinds of reductions. For instance, you have a Turing reductions that are more powerful actually, where you can use several times the result. I mean, the word x. I mean, the result f of x in the computation of b. Okay, you can use it, reuse it, and this is Turing reduction, which is more powerful.
Yeah, but A is range of.
Yeah. Okay. That's. I was just. Okay. Thank you. You're probably right. I'm unable to think anymore. So. Okay. Good. Thank you. Yes.
Maybe this is a silly question because I don't really know, but it sounds like P equals NP would imply that any NP problem could be implemented by a polydeterministic. Isn't a more basic question, is NP without P empty or?
NP without P empty. Yeah, it is the same. I think so. But
sorry, I mean, if because I'm wondering.
Actually, I could comment on this particular thing if you want. There is a theorem that says that if NP is different from P, then, okay, it just discriminates between the three possibilities, so two possibilities. Either you have, here you have NP, here you have NP complete problems, and here you have P, and you have nothing in between. Okay. Or the other scenario is that you might have NP complete problems here. You could have intermediate problems, okay, intermediate, and P here. And you can wonder if P is different from NP, either you are here or here. There are two possibilities. And actually, you can show that you are here, if P is different from NP. I don't know if it answers your question, but then there is language A, which is in NP, but not in P. Okay, this is yes, thank you. NP complete, yeah. NP, which is okay, which is not NP complete. Thank you. Yeah. Otherwise, it was just a reformulation. Okay. Yeah. Does it answer? I mean, the question.
I think yes, but I need to think about it.
Yeah. Okay.
The question wasn't well formed.
Okay. Sure.
In the third scenario, you have P equals NP equals NP complete.
P equals NP. No.
Implies.
P equals NP. Implies yes. P equals NP implies everything is NP complete. Yes, you're right. Yeah.
Is this result that you are mentioning some kind of complexity version of the existence of intermediate Turing degree?
Yes.
See Turing.
Yes.
The idea, the idea is similar.
Yeah.
Okay.
The proof is completely different.
The proof is different. The idea is similar, I would say. I mean,
Actually, it's because of that's asymptotic thing. So somehow you can. So it's not the same flavor.
Okay.
but yeah, for me, I mean, the spirit. I mean, the result is yeah. I mean, it's just a transposition of this to complexity, I would say. But indeed, the proof is completely different. Yeah.
So let's continue this during the exercise session, I would say. So thank you again, Sylvain.
Thank you.